Okay, so let us continue our discussion on dielectrophoresis for particle trapping. Okay, for the dielectrophoretic force to be effective, we said that we need to have a non-uniform electric field. Okay, and we considered a rectangular channel configuration where the gap between the plates is much smaller than the width of the plate. So, we can say that this is equivalent to a flow between two infinitely long parallel plates, and we say that we had two asymmetric electrode configuration, one hemispherical electrode at the bottom of the channel and one flat electrode on the top of the channel. So, we would be creating an non-uniform electric field. Okay. And the other requirement for dielectrophoresis is that the dielectric constant of the sphere has to be greater than that of the liquid. Okay. So, this is the case that we have been considering. We are considering a rectangular channel with height h and width w. Okay. And we said that the height is less than w, and as you can see on the right, this is the hemispherical electrode at the bottom of the channel. Okay. The hemispherical electrode, and the top electrode, this is the top electrode which is flat. Okay. So, we were saying that for the trapping, so there are basically two forces that are acting on the particle as we discussed. One is the dielectrophoretic force which is acting towards the electrode, and the other force is acting is the drag force which is trying to carry the particle with the bulk fluid. So, for the trapping, the dielectrophoretic force F dP has to be greater than the drag force. Okay. So, we consider flow between in a rectangular channel. So, we consider flow in a rectangular channel where h less than w, and we say that we can write the velocity profile uz as 6 into 1 minus z over h into z over h u0. u0 is the average velocity which is flow rate divided by the cross sectional area. So, u0 is the average velocity which is q over wh. Okay. So, the drag force, we can write the drag force F drag is 6 pi eta a into the velocity. Let us say it is ur at any location r. Okay. And this is also a vector. Okay. So, these all are vectors. Now, we need to, if you look at here, before we calculate the dielectrophoretic force, we need to calculate the electric field, and to calculate the electric field we need to know how the potential distribution is. To calculate the potential distribution in this case, since we have a one hemispherical electrode, one flat electrode, we need to guess for a mirror electrode about the top plane. Okay. So, we assume that there is another mirror electrode which is sitting at the top. Okay. So, this is the symmetry plane for the mirror. So, if we do that, we can write down the potential distribution So, the phi r will be r0 divided by the position vector r into delta v minus r0 divided by r minus 2h. So, that is along the z direction into delta v. So, that is the expression for the potential where r0 is the radius of the electrode, radius of the hemispherical electrode. Okay. So, that is going to be the expression for the potential. So, we can find out what is going to be the electric field. So, ER is the gradient of phi r, which can be approximated as r0 into delta v divided by r square along the radial direction. Okay. So, that is the expression for the electric field if you differentiate potential with respect to r. Now, if we know the expression for the electric dielectrophoretic force. So, the dP force is F dP equal to 2 pi epsilon 1 into epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into the gradient of the square of the electric field. So, it will be r0 square divided by r4 into delta v square, okay, into delta v square. So, we can simplify this to write F dP is equal to minus 8 pi into epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into a cube r0 square. Here we are missing a cube here, a cube r0 square r to the power 5 into epsilon 1, okay, into delta v square along radial direction. So, this is also along radial direction. Okay. So, since we are differentiating this with respect to r, we get a negative sign there and this becomes r to the power 5. Okay. Now, we can see from this equation that the dielectrophoretic force varies as 1 over r to the power 5. Okay. So, the maximum dP force would be realized when r is minimum, and the minimum r is going to be the radius of the hemispherical electrode plus half of the size of a particle. Okay. So, that is going to be the minimum radial distance from the center of the hemispherical electrode to the center of the particle. Okay. So, what we see from here is that the dielectrophoretic force varies as 1 over r to the power 5. Now, for the dielectrophoretic force to be maximum, r has to be minimum. So, here r minimum, and the r minimum is, so we have a hemispherical electrode. Okay. Now, this is the center of the hemispherical electrode, and this is where we measure R. Okay, R goes in this way, and let us say we have a particle sitting here and which has radius a. So the minimum R is going to be this, okay, and this is nothing but a plus R. So R minimum is going to be the radius of the particle plus the radius of the hemispherical electrode, okay. So so the R minimum is R0, so this is R0 not R, so this is R0 plus A. We can say that this is 1 plus gamma into A. Let us define gamma as R0 over A. So, the ratio between the radius of the electrode to the radius of the particle. So, with that we can substitute this R minimum in the dielectrophoretic force equation here to find the maximum dP force. So, the maximum dP force F dP max can be F dP R min, which is going to be 8 pi epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into gamma square divided by 1 plus gamma to the power 5 epsilon 1 into delta V square. So, that is going to be the expression for the maximum dP force. Okay. So, we are actually taking the magnitude. So, the negative sign has dropped off. Okay. Now, we are interested to see what is the maximum velocity with which we can transport the sample, at the same time we are able to trap the particles from the sample. Okay. So, the maximum dP force is going to be when the R is going to be R0 plus A. Okay. So, we can find out what is going to be the drag force at that location. Okay. So, first we find the velocity at R equal to R0 plus A. So, that is going to be, so U R0 plus A is equal to 6 into 1 minus 1 plus gamma into A over H into 1 plus gamma into A over H U0. Okay. So, that is the expression for the velocity if you substitute R as R0 plus A. So, this is what you would get. So, U R0 plus A, you can simplify this to 6 into 1 plus gamma into A over H into U0. Okay. Right. So, from knowing the velocity you can find what is the drag at this location. So, drag force at R equal to R0 plus A is going to be F drag R0 plus A. So, finding the magnitude is going to be 6 pi. So, 6 pi eta A and U R0 plus A. So, we have already an expression for U R0 plus A. So, this is going to be 36 pi into 1 plus gamma into eta a square over h into u0. Okay. Now, for the trapping to be possible, the drag force has to be less than the dielectrophoretic force. So, in the limiting case, let us say the F dep is equal to F drag. Okay. So, the maximum velocity at which trapping is still possible. So, F drag will be equal to F dp max. Okay. So, we have an expression for the drag force where the dp force is maximum, and we have an expression for the maximum dp force. So, we can write the drag force is 36 into pi into 1 plus gamma into eta a square over h u0, that is maximum velocity that we are interested to find out is going to be 8 pi epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into gamma square divided by 1 plus gamma to the power 5 epsilon 1 delta v square. So, from here we can find out what is going to be the maximum velocity. So, u0 max is going to be 4 by 9 into epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 gamma square plus divided by 1 plus gamma 6 h epsilon 1 delta v square over eta a square. Okay. So, that is going to be the maximum velocity of the particles or the samples at which trapping is still possible. Now, let us consider a test case. We consider a test case where we have liquid benzene as the medium. Okay. And the properties are the dielectric constant epsilon 1 is the permittivity is 2.28 into permittivity of free space, and the viscosity is 0.65 millipascal second, and let us say we have glass particles. Okay. So, we have glass particles that we are trying to trap from liquid benzene. So, we have glass particles whose permittivity is 6 times permittivity of free space, and let us say the radius of the particle and the radius of the hemispherical electrode, they are the same, is about 5 micron, and let us say the channel height h is 100 micron, and the applied voltage delta V is 10 volts. So, under that condition we can find out that the velocity u max is going to be about 30 millimeter per second. Okay. So, such a velocity is actually considerably high in microchannels. So which is very encouraging, because the trapping is still possible at such higher velocities in a microfluidic environment. Okay. So but one necessary condition for dielectrophoretic force is that always the dielectric constant of the particle has to be higher than that of the liquid. Okay. So such higher velocity is encouraging. The one necessary condition is that the dielectric constant of, or the permittivity of the medium has to be greater than the permittivity of the liquid. Okay. So now what we have done here is we have taken an example of the electrode configuration, but depending on the electrode configuration that we have for a specific problem, we can determine what is going to be the potential distribution, what is going to be the electric field, and accordingly we can find out dielectrophoretic force and balance it with the drag force to calculate what could be the expression for the maximum velocity. Okay. And from there, for a given set of conditions, we will be able to find out what could be the flow rate at which we can drive the sample, but still achieving trapping of the particles present in the sample. Okay. So with that, let us move on to talk about AC dielectrophoresis. So what we have been looking at in dielectrophoresis is DC dielectrophoresis. Okay. However, the AC dielectrophoresis have certain advantages. Okay. The first advantage is that the charged monopoles or the ions will not move with respect to their original position in case of a AC dielectrophoresis, because the polarity of the electrode will change. So any drift of an ion in the first cycle will be compensated by the second cycle. So the ions in the liquid will not move relative to its mean position. Okay. So the charged monopoles or ions do not change mean position in AC fields. Okay. Now the second advantage is that when we talk about the electrodes that we use to achieve dielectrophoresis, we know that when we have a charged surface and we have a liquid that has non-zero electrical conductivity, will result in forming what is called Debye layer. Okay. So in case of DC dielectrophoresis, we have permanent Debye layer forming over the electrodes. Okay. So which is not a good sign for the dielectrophoretic force to continuously occur for a longer time. Okay. And by going for AC dielectrophoresis, the permanent Debye layer formation on the electrodes is prevented. Okay, because there is always a change in the polarity in each cycle. So there is not enough time for the Debye layer to be consistently there for a longer time. Okay. So what we have is the creation of permanent Debye layer at electrodes avoid it. Okay. The third advantage of the AC dielectrophoresis is that the Clausius-Mossetti factor in DC dielectrophoresis is depends on the dielectric constant of the liquid and the particle. In AC dielectrophoresis, the Clausius-Mossetti factor is also dependent on the driving frequency, okay, of the signal. So, what this enables is that by manipulating the frequency of the signal, we would be you can achieve in situ trapping or release. Okay. So, by controlling the driving frequency for a fixed set of particle and liquids, we can vary the sign of the dielectric force. Okay. So, selectively we can trap, we can release particle in situ. Okay. So, that is possible in AC dielectrophoresis. So, in AC dielectrophoresis, the Clausius-Mossetti factor depends on the driving frequency. Okay. So, what this means is, so this is let us say driving frequency omega, and the Clausius-Mossetti factor can change sign. Okay. And hence the dielectrophoretic force can also change sign. So, this enables in situ control is possible. So, selectively attractive or repulsive force is possible, attractive or repulsive force possible. Okay. Now, if we consider a simple harmonic variation, so if we consider simple harmonic time variation, so something like exponential minus I omega t. Okay. We can express the potential phi RT as phi r into e to the power minus I omega t, and we can write the electric field as e to the power minus I omega t. So, these are we are considering that the potential and the electric field following the simple harmonic time variation, okay, as you can see there. Now, when we deal with simple harmonic time variation, we can have AT, for example, will be the real part of A0 e to the power minus I omega t. Okay. And we can define Bt as the real part of. So, these are equivalent to our expression for potential and electric field. We are giving an example where, so this is the time dependent variation A, this is B, the real part of B0 e to the power minus I omega t, where A0 and the B0 are called the constant complex amplitudes. Okay. So, we can have time average of AT and BT time average of AT and BT is going to be half of the real part of A0 into B0 star, okay, where B0 star is the complex conjugate of B0. So, in AC dielectrophoresis, since we will be talking about harmonic variation of the signal, we would be requiring these details while we talk about time average of the dielectrophoretic force. Okay. So, we would require how we can do the time averaging of the dielectrophoretic force from these basics that we look at here. Okay. Now, we can generalize the expression for dP force, the expression of dP force for AC fields, and here we say that the liquid has non-zero electrical conductivity. Okay. So, for that we would require the general boundary condition, which is nothing but that the electric field in the radial direction ER r theta, okay, at a location r and along theta is minus del over del r into phi r theta. So, this is the simple definition of the electric field with respect to the potential. So, which acts as the boundary condition in the radial direction, okay, and this boundary condition is at the surface of the sphere or the particle, surface of the sphere or particle. Okay. So, we can write, if you remember, we had written the boundary condition for DC case epsilon 1 E r 1 a theta t. So, in DC case we did not have t, we had a and theta, which will be equal to epsilon 2 E r. Okay, so this should be minus a theta t is equal to the charge density. Okay. For DC case we did not have the charge density. So, epsilon 1 E r 1 a theta was epsilon 2 E r 2 a theta, okay, that was the boundary condition that you used in DC case. Now, here we have AC, so time is coming into play, and here also we are assuming that the liquid has non-zero conductivity. So, there is some charge density on the surface, okay, which is taken into here. So, if you have perfect dielectric medium, then the Q surface is 0, and this was the case we considered in DC, okay, DC dielectrophoresis, and with non-zero conductivity, and AC fields, the Q surface is not equal to 0, and this is going to be time dependent. So, the surface charge is going to vary with time, it is time dependent. Okay. So, this is the boundary condition we are going to use in AC dielectrophoresis. Let us call this equation A. Okay. Now, this time dependent charge q surface can be given by the charge conservation, okay, by the Ohm's law. So, the q surface, which is the charge on the surface, is given by charge conservation and Ohm's law. Okay, which is given by the del q surface, which is a function of time, over del t is going to be j r1 a theta t minus j r2 a theta t. So, this j is nothing but current density, right. We have looked at this in electrohydrodynamics. This is nothing but current density, okay, and we can write current density in the form of electrical conductivity and electric field. So, if you do that, we write electrical conductivity of 1 and electric field ER1 a theta t minus electrical conductivity of 2 E R2 a theta t, okay. So, that is how the charge on the surface is going to vary with time, and if we express that in terms of the electrical conductivity and electric field in the medium as well as in the sphere or particle. Let us call this equation as equation B. Now, if we take time derivative of equation A, okay, you divide both side with d by dt, we take derivative d by dt on both sides and plug that in this equation, okay. So, you take the time derivative here dq surface over dt. So, we get time derivative of the left side, and then in place of dq surface over dt, if you plug in this term on the right hand side, then this is what we will get, okay. So, we take time derivative of equation A and substitute equation B, okay, and after substituting we, so if you do that first and then multiply with I over omega, okay. If you do that, we get this equation, we get epsilon 1 minus I electrical conductivity 1 divided by the frequency into E R 1 a theta will be equal to epsilon 2 minus I sigma of 1 divided by W E R2 a theta. So, this is the equation we get when you do the above, okay. So, here we can define a complex dielectric function, complex dielectric function, which is epsilon omega is going to be epsilon minus I into sigma over omega. So, if you define that, then this equation will be something like epsilon 1 into the electric field E r1 a theta, okay. Sorry, this will be epsilon 1 omega, right, will be equal to epsilon 2 omega epsilon r2 a theta. So, this equation is similar to what we had seen for the DC case, except that the dielectric constant is replaced by the complex conjugate of the dielectric constant, okay. So, we have a solution for the dielectric force for the DC case, and if you modify the Clausius-Mosetti factor to include the complex dielectric constant instead in place of the dielectric constant itself, then we can get an expression for dielectrophoretic force for AC case, okay. So, what you do is, so the result for DC case can be used with complex dielectric function in the Clausius-Mosetti factor. Okay. So, this we can do, because this equation is similar to our DC case where we saw epsilon 1 E r1 equal to epsilon 2 E r2. So, this is what we saw in DC, okay. So, the only difference is that this dielectric constant is replaced by the complex dielectric function, okay. So, we can write down the dielectrophoretic force for AC case, which is a function of, let us say, at r0 t, okay. This is going to be 2 pi epsilon 1. So, make it, please note that this dielectric constant is going to be the dielectric constant of fluid, okay, not the complex dielectric function. Only the expressions in the Clausius-Mosetti factor becomes complex. So, this will become epsilon 2 omega minus epsilon 1 omega divided by epsilon 2 omega plus 2 epsilon 1 omega to a cube into gradient of E r0 t square, okay. So, this is the dielectric constant of medium, not complex dielectric function, okay. So, this is going to be the expression for the dielectrophoretic force in AC field, okay. Now, this is time dependent. So, we have to find a time average dielectrophoretic force. So, you can find the time averaged dp force, okay, which is F dp. Now, here if you look at what we had seen earlier. Okay, we had AT and BT. So similarly here we define AT as the Clausius mortality factor K of epsilon 1 omega epsilon 2 omega, which is nothing but this term there, okay, into E R0 t, and we have another term to define BT is E of R0 t. So these are two functions, okay, from the dielectrophoretic force that we can extract that are time dependent, okay. So we can average the dielectrophoretic force similar to the time average of AT/BT. You can find F dep R0 omega is going to be 2 pi epsilon 1, the real part of the Clausius mortality factor omega epsilon 2 omega. So real part of this term into A cube and to the gradient of ERMS square R0. So this is the root mean square electric field where E RMS is going to be epsilon over square root of 2, okay. So this is going to be the expression for the time average dielectrophoretic force, okay, in the AC mode. Now we have to find that what is going to be the critical frequency about which this dielectric force is going to change its sign, okay. From positive this may become negative, and as you know that the change of the sign is going to be decided by the value of the Clausius mortality factor, because that is the only term which has the control over dielectrophoretic force, okay. So if you want to find the critical frequency at which the dielectrophoretic force sign changes, then we have to say that this part, so this the real part of the Clausius mortality factor will change between negative to positive, okay, and to find the critical value let us equate that to 0, okay. So if you do that you can write the real epsilon 2 omega c and we take to this to the numerator plus 2 epsilon 1 omega c star, that means that is the complex conjugate is going to be 0. So if that is 0 then we can find the critical frequency, okay. So what we see here is that this part can control the sign of the dielectrophoretic force. So we say that this part can move from negative to positive, okay. So since it moves from negative to positive at the critical value this would be 0, okay. So that is what we are doing here, and if that is 0 you can find the critical frequency, which is going to be electrical conductivity 1 minus electrical conductivity 2 into electrical conductivity 2 plus 2 electrical conductivity 1 divided by epsilon 2 minus epsilon 1 into epsilon 2 plus 2 epsilon 1 square root of that. So, the critical frequency is going to depend on the electrical conductivity of the medium and the particle and the dielectric constant of the medium as well as the particle. Okay. So, the critical frequency at which the dielectric constant will change sign will depend on the electrical conductivity and the dielectric constant of the medium as well as the particle. Okay. Now, if we consider a biological cell, and the biological cells have mainly cytoplasm in water. Okay. So, we have mainly cytoplasm in water. So, the electrical conductivity of the medium is 0.1 Siemens per meter, and epsilon 2 is 60 times epsilon 0, and that is for the cell. Okay. And for the medium, which is water, we have 0.01 Siemens per meter, and epsilon 1 is 78 times epsilon 0, this is for water. So, we have the particle and the medium. So, for this case, if we find the critical frequency, the omega c turns out to be 1.88 into 10 to the power 8 radian per second. Okay. So, that is typically the value of the critical frequency. Okay. What is interesting about AC dielectrophoretic phoresis is that the Clausius-Mossetti factor is dependent on the frequency. Okay. And that critical frequency is dependent on the property of the medium and the property of that object. Okay. So, this can be used to can be exploited in biology to separate living cells from dead cells and cancerous cells from healthy cells, because the electrical conductivity, the dielectric constant are different for healthy cells and diseased cells, and they are different for living cells and dead cells. Okay. So, the critical frequency is going to be different for the different types of cells, and this can be exploited to separate them. Okay. So, what we know from here is that the frequency dependent dp force can be used to separate living cells from dead cells, okay, and healthy cells from cancer cells. Okay. and this is because the different cells have different sigma and epsilon, and so this gives rise to different omega c. Okay. So, the omega c at which they are captured or repelled is different for different cells, different cell types. Okay. So, this has interesting applications in microfluidics.